Next, we're going to move up to 5 regions of electron density, and we're going to first look at the case where we don't have any lone pairs. An example of that would be PCl5, phosphorus pentachloride. Here's the Lewis structure. I'm going to leave off the lone pairs and the chlorines just to make life simpler. I've got 5 regions of electron density around this central phosphorus, and they're all bonds. My VSEPR arrangement, when I have 5 regions, is a trigonal bipyramidal. The molecular shape is 2, because every one of these is a bond. So I've got my equatorial bonds, and I have axial bonds, so the molecular shape is also a trigonal bipyramidal. This is the shape of the molecule itself. Here's phosphorus in the middle, chlorine here, chlorine here, chlorine here, chlorine here, and chlorine here. We can draw this. There's a sort of a stylized way to draw this. You kind of draw a tipped over triangle, put your central atom in the middle, and then put your outside atoms on your equatorial plane. You can sort of sketch in those bonds, and then go up with an axial, and then go down with an axial, and like show it hidden by making a gap there. And that's a sort of way to draw this if you're not a good artist. Now let's take a look at 5 regions of electron density with 1 lone pair. An example of this would be sulfur tetrafluoride. If you draw the Lewis structure for sulfur tetrafluoride, again, I'm going to leave the lone pairs off of the outside fluorines. This is what you end up having to do. You have to have an extra pair of electrons in the central atom. It's an expanded octet. Well, you've got 5 regions of electron density, 4 bonds and 1 lone pair. So that means our VSEPR arrangement is going to be trigonal bipyramidal. But the molecular shape isn't. Now, where would we put our lone pair? Remember, lone pairs are more repulsive than bonds. So we want to put it in a place where there's the most room possible to spread out. The equatorial bonds are 120 degrees apart from each other, and the axial bonds are 90 degrees away from the central plane. So there's more room in the equator. So that's where our lone pair is going to go. Now, the molecular shape that we get is based on this. There's a bond there, a bond there, a bond there, a bond there. This is like the fulcrum, and this is like a seesaw, and that's the molecular shape. Seesaw. Sophisticated people might call that an asymmetrical tetrahedron, but seesaw is pretty descriptive. Here's a picture of the molecule. Again, here's the base of the seesaw right there, that set of bonds, and there's the seesaw itself that the kids sit on. And in the example that we use, this would be the sulfur. There's fluorine there, there's fluorine there, there's fluorine there, and there's fluorine there. Seesaw. Now let's take a look at an example where we have 5 regions of electron density and 2 of them are lone pairs. An example of that would be ClF3, which has this Lewis structure. Cl in the middle, 3 F's on the outside. Again, I'm leaving off the lone pairs on the outside fluorines. And now I've got lone pair, lone pair. So there are 5 regions of electron density, 2 of them are lone pairs. Again, there's more room in the equator than there is on the axials, and so maybe I'd have lone pair there, and then here are bonds. Bond there, bond there, bond there. All these bonds are 90 degrees from each other. The VSEPR arrangement, of course, is trigonal bipyramidal. But the molecular shape was very simple. It looks like the letter T, and so we call this a T-shaped molecule. There's a picture of the molecule itself. For the example we were using, here's chlorine in the center, fluorine, 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 and then we have lone pairs there and there. You might even have the case where you have 5 regions of electron density and 3 of them are lone pairs. Well, the valence shell electron pair arrangement is, of course, going to be trigonal bipyramidal because there are 5 regions of electron density. Here's an example of such a species, the I31- ion. It's a polyatomic ion with 3 iodines, sort of an obscure ion. Lewis structure looks like this. I have I bonded to 2 other I's, and then there are 3 lone pairs. So that means a total of 5 regions of electron density, but 3 of them are lone pairs. Well, there's more room in the equator for these more expansive lone pairs, and so they're all 3 going to go there. And the molecular shape that you end up with is just linear. Picture the molecule itself. Iodine, another iodine, another iodine. and then bonds in between. So all you see is a straight line, but it's a straight line because of the fact that these three are lone pairs. Now let's move up to 6 regions of electron density. First of all, we'll take a look at the case where we have 6 regions of electron density and they're all bonds, no lone pairs. Like, for example, sulfur hexafluoride. Lewis structure looks like this. Outside fluorines, I'm leaving off the full octets again just for simplicity. 6 regions of electron density, all of them are bonds. The valence shell electron pair arrangement, when you have 6 outside regions, is always going to be octahedral. And because all of these are bonds, the molecular shape is also called an octahedral. So bond here, bond here, bond here, bond here, bond here, bond here. Bonds to fluorines on the outside, sulfur in the middle. Everything's a bond. Picture the actual molecule. There's a sulfur, fluorine there, fluorine there, fluorine there, fluorine there, fluorine there, and a fluorine there. Again, there's a stylized way to draw this, sort of a tipped over rectangle or tipped over square. Put your central atom in there, and on the corners of this central plane, if you will, you put your outside atoms, and then go up with one, and again go down with one, showing that little gap there to show that it's sort of peeking out from underneath there. Now let's take a look at a case where you have 6 regions of electron density and one of them is a lone pair. An example of such a species is BrF5. So the Lewis structure for this looks like this. Br, 5 fluorines on the outside. Again, I'm not filling their octets for simplicity. And then there's a lone pair. Now we have 6 regions of electron density. 5 of them are bonds. 1 of them is a lone pair. Because there are 6 regions, the VSAPR arrangement is octahedral. But the molecular shape was influenced by the fact that right there, let's call this one down there, a lone pair. So it's just because it's 5 regions doesn't mean it's going to be trigonal bipyramidal. In this case, it's something different. If you think about what we've got here, there's an atom there and an atom there. Connect those two together. An atom here, connect those two together, and that's together. This atom here, I can connect there and I can connect there. And this atom that's here connects up there, connects over there, connects over there. And what we've got is a pyramid with a square base. So this molecular shape is called a square pyramidal. Here's the molecule itself. For the example we were looking at, Br here, fluorine here, fluorine here, fluorine here, fluorine way in the back, and fluorine here on top of my finger. Now let's take a look at 6 regions of electron density with 2 lone pairs. An example of this would be an unusual molecule called xenon tetrafluoride. Xenon, remember, is a noble gas, and they're not supposed to react, so you can tell that that's a little bit of a lie. It is possible to get them to react. It takes some effort, though. Now, here's the Lewis structure for xenon tetrafluoride. Got a central xenon, have 4 fluorines on the outside. Once again, I'm leaving off their octets. But the full octet is not enough for all the valence electrons, and so I had to end up putting 2 lone pairs in there. So I have 6 regions of electron density, which means that the VSEP arrangement is octahedral again. But 2 of them are lone pairs, so let's say lone pair up here. Now, it matters where I put my other lone pair, because they're more repulsive than bonds. I don't want to put it 90 degrees away from this lone pair, so I'm going to put it 180 degrees away from that lone pair. The molecular shape, then, is flat. I got 2 lines that intersect right at the center, and that's called a square planar, because the outside atoms make a square, but it's a flat plane. So the molecule actually looks like, here's my xenon atom, fluorine, 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 and fluorine. 90-degree angles all around in the square planar. Let's work out a few examples of these so you can go from beginning to end. Here's SbH3. Let's try SbH3. The first thing we want to do is draw a Lewis structure, because that's the basis of all of our decision making about molecular shape. So I'll find out how many electrons I have to work with. Well, antimony is in column 5, and so that's going to give you 5 electrons. And then I've got 3 from hydrogens, because there's 3 of them, and it's in column 1. So that gives me 8 electrons total. When I draw my structure, put an antimony in the middle, Hydrogens have to go on the outside, and the only full octet I need is on antimony, so I put that there. Then when I count, I've got 2, 4, 6, 8 electrons, which is how many I'm supposed to have. So there's the structure for antimony. Now, here's what this tells me about shape. I've got 4 regions of electron density, and one of them is a lone pair. So I could categorize this as an A, B, 3, E structure, if I'm into that code thing, because I have a central atom, 3 outside atoms, and 1 electron pair. Or I could visualize the shape. If I have 4 regions of electron density, that's going to be tetrahedral. With 1 lone pair, that gives me a trigonal pyramidal shape. Let's do another example. PCl4 1+. This is a polyatomic ion. Well, phosphorus is in group 5, so that's 5 electrons. And then chlorine's in group 7, so that'd be 7 electrons, but 4 times would make that 28 electrons. 5 and 28 is going to add up to 33, but this is a 1+ ion. So because of that, I'm going to take away 1 electron and settle on 32 electrons in my structure. Here's my skeleton, phosphorus in the middle. I'm going to put the 4 chlorines on the outside, sort of as the formula indicates. Fill octets, phosphorus is already good. Each chlorine gets 6 more electrons, 3 pairs, and then I'll do my count. There's 6 here, 12, 18, 24, 26, 28, 30, 32. So that's the correct number. I'll finish up my structure here because this is a polyatomic ion by putting brackets at charge. Now, how about the shape? If I take a look at the central phosphorus, it's got 4 regions of electron density, and those are all bonds. And when that's the case, we have a tetrahedral molecule. You could also think of this as an AB4 if you're using the code thing, and that indicates to you also that it's tetrahedral. Well, we're at the working it out phase here, and so it's time for you to make a prediction. Stop the video and try and predict the shape of ClO3 1-. Here's your answer. Chlorine is in column 7, so that gives you 7 electrons. Oxygen's in column 6. 3 of those would give you 18 electrons, but it's a 1- ion, so I have to add 1 more electron to the count. 7 and 18, it's 25 and 1, so I'm going to have 26 electrons in my structure. This is counter to some of our rules for skeletons, but the formula indicates that the central Cl will have 3 O's around it. When I fill octets, I have to put a pair on chlorine and 3 pairs on each of the O's. When I do my electron count, I have 2, 4, 6, 12, 18, 20, 22, 24, 26. So that's the correct structure. I'll finish off with square brackets and charge. Looking at the central atom, the chlorine, I've got 4 regions of electron density, and 1 is a lone pair. By code, that would make this an AB3E, and it's a 4-region of electron density shape with 1 lone pair. That tells you it's a trigonal pyramidal. Okay, try this one. Predict the shape of SiO4 4-. Here's your answer. Silicon's in column 4, so there's 4 electrons. Oxygen's in column 6. 4 of those will give you 24 electrons. And it's a 4- ion, so I need to add 4 more electrons. So this gives me a total of 32 electrons. Put silicon in the middle, arrange my O's around the outside, and fill octets. Silicon's already good, but each of the oxygen needs 3 more pairs. Now when I count, got in lone pairs around oxygens 24, 26, 28, 30, 32. So square brackets and charge to finish this up, and then I want to look at my shape. I've got 4 regions of electron density, so it's an AB4, or if you just think about the shape, 4 regions of electron density are arranged in a tetrahedral molecule. There's another one, BrF4 1-. Stop the movie and give it a shape. Here's your answer. Bromine is a halogen, that's 7 electrons. Fluorine's also a halogen, 7 electrons 4 times is 28. Plus it's 1-, so we add another one. So this gives us a total of 36 electrons in the structure. I'll put Br in the middle, like the formula indicates, and put my 4 fluorines on the outside. Bromine already has a full octet, but the fluorines each need 3 pairs. If I do my count, we've got 2, 4, 6, 12, 18, 24 with the lone pairs, 26, 28, 30, 32. and I still need 4 more electrons because I'm supposed to have 36. So I'll put them in the central atom, or on the central atom in pairs. Alright, this now gives me 6 regions of electron density with 2 lone pairs. The code for that is AB4E2, or you can think about 6 regions of electron density as being octahedral, but with the 2 lone pairs in there, it's going to be a square planar molecular shape. Try to predict the shape of TeF6. Well, here's your answer. Tellurium, Te is in column 6, like oxygen, so that gives you 6 electrons. Fluorine's column 7, halogen, so 7 times 6 is 42. So this structure should have 48 electrons in it. Skeleton should put Te in the middle, put my 6 fluorines on the outside, and then I'll fill octets and count at the same time. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, and then I go to the bonds, 38, 40, 42, 44, 46, 48. So that's the correct structure. Looking at the central tellurium, it's got 6 regions of electron density. They're all bonds, so this is an octahedral molecule. If you go by the code, this is an AB6, which should tell you octahedral. Let's take a look at this little movie. I'm going to have the shapes pop up here. See if you can identify them. Be a little way to review.